Now, light is a wave, and light is a particle of energy. In reality, it's sort of some combination of both of these ideas. It's easier usually to think of it as either a wave or as a particle, depending on the situation, but it is in fact both. And here's some evidence showing you that it is got properties of both at the same time. It's kind of a wave and a particle at the same time.
Here we have the source of light over here. And it's passing through two slits, but we've had to cover this up because we don't want any light to get in. The light passes through the two slits, goes over to the other side. Instead of a screen over here, we've actually got a camera because this detects really low levels of light. I'm going to see what we see. Actually, up there on the screen, you can see what the camera's picking up. The first surprise is it's picking up dots, blips. This is light traveling through this, but it's arriving as blips, like the sand, as particles. So that's amazing. But have a look at this. If we collect up all these blips, collected over a time period, and have a look at what the pattern is, we see something quite remarkable. The pattern you see is the pattern that waves make. But the light arrives in blips, in packets, as small particles, which physicists call photons. So this is incredible, because the light's traveling, making a pattern as though it were going through two slits. Because remember, to make that pattern, that wave pattern, there've got to be two sources, two slits. The light's got to go through both slits. And yet it's arriving as a blip, as a particle, like the sand. This is the essence of the weirdness, of the spookiness in the quantum world.
So light is both. It is a particle, it is a wave. Sometimes we think of it as a particle, sometimes we think of it as a wave. But if you wanted to try to imagine what it looks like as both a particle and a wave at the same time, here's sort of the way I see it, and one of the ways a lot of scientists kind of see it.
The moving charge of the electron creates an oscillating magnet field, which creates an oscillating electric field perpendicular to it. These two fields move themselves through space, transferring energy from one place to another.
So the entire electromagnetic spectrum is waves. All of these lights have wavelengths. They also have frequencies, but they're also little packets of energy. And as you can see on this chart here, it actually has the energies down here at the bottom as well. And the high frequencies have higher energy. These are also the short wavelengths. The low frequencies, which have long wavelengths, have very little energy. Okay, so we can actually get some pretty high energies here with these gamma rays, and that can be pretty dangerous. You will notice that the higher energy would be the violet end of the spectrum. This is going to be the high frequency as well, but the lower wavelength. The red end of the visible spectrum is where we get the lower energies, the lower frequencies, and the longer wavelengths. Now, the smaller it gets, the smaller it gets in wavelength, the higher the frequency. The higher the frequency, the more energy it takes to create it. If you think about it, if I wanted to create a wave, say, in a pool, and I go up and down to make it. Now, I'm basically making waves in that pool. If I want to make more waves, okay, they would be shorter and they would be faster. I would have to move even faster to make more waves, and that causes more energy. It takes more energy for me to do that. So the more waves I'm making in a second, the more energy it takes to make them, so the more energy those waves have. So these really, really short wavelengths like UV and X-ray and gamma, they have a lot of energy in them. They take a lot of energy to create, and they propagate a lot of energy. You absorb a lot of energy from them if they were to hit you, which is what makes X-rays and gamma rays and UV more dangerous than the rest of these. Okay? Now, combining the two ideas of both photon and wavelength, you can have both equations kind of happening at once here. So what is the wavelength of a photon of light that has 4.41 times 10 to the power of negative 19 joules of energy? First off, this is using the word photon, and it gave us energy. So this is all about the photon model of light, kind of that photon idea, particle of energy here. However, it asks for wavelength, and wavelength is not a part of that idea. Okay? So we can combine the two ideas and figure this out, what's the wavelength, by kind of thinking it first as a photon and then as a wave. So let me show you how this works. Okay, so in this problem, I'm going to treat it like both a photon and a wave. So I'm going to divide my paper in half. This side is going to be the photon side. This side is going to be the wave side. All right, now for a photon, the equation is E equals Planck's constant times the frequency. Energy equals Planck's constant times the frequency. For the wave side, the speed of light is equal to the wavelength times the frequency. All right? So two equations, one for photon, one for wave. Now it's giving me joules of energy here, 4.41 times 10 to the power of negative 19 joules of energy. There is no energy for the wave. It's all about the photon for the energy. It's a packet of energy here. So this number is only going to be useful for the photon, and it's telling me it's a photon, so that's right where I'm going to start. Okay, so I know the energy. I also know Planck's constant. The thing I don't know is going to be the frequency. So I'm going to find the frequency here. So I'm going to plug in the energy, 4.41 times 10 to the power of negative 19 joules, is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules seconds, times the frequency, which I don't know. Getting kind of tight there, sorry. Now, isolate x here, so I'm going to divide both sides by Planck's constant. So divide by 6.626 times 10 to the power of negative 34 joules seconds. Do the same on this side. Okay, that cancels this, so the only thing left is the thing I don't know. So I'm going to plug this side into the calculator here. 4.41, second e to the power of negative 19, divided by 6.626, second e to the power of negative 34. And I get 6.655599 times 10 to the power of 14. Don't forget that power there. So this is three significant figures, so I'm going to stick with that. 6.65, actually that rounds up to a 6, 6.66 times 10 to the power of 14. The unit here, joules cancel, so it is per second, okay, or hertz. All right, now that is the frequency. The question asked for wavelength. All right, I don't have wavelength as part of this equation, but I do in the wave idea. So I do know the speed of light, and I want to know the wavelength. I also, though, didn't know the frequency, but now I do know the frequency. It's 6.66 times 10 to the power of 14. So now that I know the frequency, the only thing here I don't know is the wavelength. So I can switch over to the wave idea here. The speed of light is equal to 3.00 times 10 to the power of 8 meters per second. This is equal to the wavelength, don't know it, times the frequency, which I just figured out. That was 6 point, and it's sometimes a good idea to just use your original number here. So 6.55599, blah, 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 times 10 to the power of 14 per second. Okay? So in order to isolate x here, I'm going to divide both sides by that number. So I'm going to take 6.55599, blah, 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 times 10 to the power of 19 per second. And that will make that go away. So all I'll be left with is x. Okay? So x equals this divided by this. So 3.00 second e to the power of 8 divided by, and then I'm just going to use that number, previous answer, equals 4.507. I get three significant figures here, so 4.51 times 10 to the power of negative 7. And the unit here, since the per second cancels, is going to be meters. So the wavelength is 4.51 times 10 to the power of negative 7 meters. Now, a common question that I ask sometimes is, what color of light is this? Like, what color would that be? We know the wavelength of it. So, colors for light that we can actually see is usually not given in meters. It's usually given in nanometers. So I'm just going to real quick convert this to nanometers, into the negative 7 meters. There is, in 1 meter, 10 to the power of 9 nanometers, so that would be 451 nanometers, okay? So if this is 451 nanometers, and I look at the spectrum here, so what color of light is this? Well, 451 would fall about, this is 450, so about right here. So this would happen to be sort of a dark blue color, right? So almost indigo, but kind of this dark blue area, somewhere about right here. So blue.